welcome everyone to this week's Algebraic Graph Theory seminar. Today we have two speakers, Sabrina Lato from the University of Waterloo and Christino Tamon from Clarkson University, and they're going to tell us about monogamy violations in perfect state transfer.
Okay, thanks the organizers for having both of us. As I mentioned before, we like the talk to be interactive, so please interrupt and ask questions as much as possible. Okay, so Sabrina and I are going to go back and forth. So the plan is, so let me scroll to the next page. Oops, that is not. So I apologize. This is, yeah, so this is the outline. So the plan is to cover some fun facts about quantum walks. And then, so both myself and Sabrina will do this. And then Sabrina will tell us about PST on oriented graphs. And then I will say something about universality in PST. And then we'll conclude with open questions. Okay. So this is going to be, we're going to try a board talk, so please bear with us. And so let's start. Okay, so, and please let us know if there's something that's not clear, not legible, or something is off. Okay, so let's start. So we start with a graph. So is this legible enough? Is this okay? Right, so okay. So we start with a graph, G, and typically it's simple and undirected. Okay. So for example, classic example is just that. And we also have the adjacency matrix. Corresponding to the graph, and in this case, will be just this real symmetric. So sorry, so this is will be 0, 1 symmetric.
Tino.
Yeah.
Would you be able to make the pen just a little bit thicker?
Yes, I think so. So so let me see. So I did have a pen option. Here we go. What about thick symmetrics? Is that better?
Yeah, I think that's better.
Actually, yeah. Okay. Good. Good. Okay. Right. So this is typically a real symmetric matrix that we play with, and what we'd like to look at is a process called continuous time quantum walk. And essentially, what we like to analyze here is essentially a process that takes the exponential of this matrix. So this matrix is unitary and symmetric as well. It has complex entries, but it is unitary and symmetric. So the explanation for this is we essentially use spectral decomposition of this matrix, and that is usually just the okay. So in this case, we have. So I'm just going to write this because I'm going to use it later. So we can just take the outer product of the eigenvector corresponding to this eigenvalue. So this is an eigenvalue of this matrix. And then there's another eigenvalue, which is -1. So we take the outer product of the eigenvector as well. Okay. And if we check this, then you can see that this is actually just this. eigenvector. Yeah. So the nice thing is this spectral decomposition allows us to analyze this exponential matrix by simply just exponentiating or performing this function on the eigenvalues. So this essentially will give us something like this. All right. So we just apply the function to the eigenvalues. And so let's call this matrix C of t. So t is a time parameter that's typically non-zero real, non-negative real, excuse me. And if we check this, then this should come out to be something like cosine t minus I sine t minus I sine t cosine t, which you can just check this. So is this okay so far? Please interrupt if there are any questions. Okay. So the thing that we're interested in looking at is notions of state transfer. And essentially here the question is, so we ask several kinds of questions. The first question we can ask is, okay, so if I call this vertices A and B, we would like to ask in general, this unitary matrix here, if we were to start with the unit vector centered at A, does this unitary map send this to itself, for example? So the question here is, does it return? So is there a time so that this unit vector comes back to itself up to some phase? Because it's unitary, might introduce a phase, so which we will ignore typically. So the answer to this is yes. If we take time equals pi, because if we peer through this matrix, this matrix at time pi looks like -1, 0, 0, -1. Okay, so that means if we multiply, so essentially we're just looking at the first column because this is indexed by A. So yes, with a phase of -1, it comes back to itself. Okay. So this unit vector actually comes back. Is this okay? So this property is something we call periodic behavior. All right. So second kind of question, type of question is we ask is it true that the walk, does it visit B? So does A visit B, if you like? So here the question is, if we were to start with this unit vector, does it get to the other unit vector through this unitary map? And the answer here also is yes, on another time. So on this other time, we would have 0 minus I, 0. So notice this matrix is complex, might have complex entries, but it's symmetric. So if we peer through this first column here, up to a phase of -I, it does send this unit vector to the other unit vector. In this case, we say there's a perfect state transfer. from A to B. So let's say this is the notation we'll use. And the time is pi over 2. And here periodic essentially is A to A, if you like. You can argue this is also a PST, but time pi. Okay, okay, good. Some observations, some quick observations, is that if we have PST from A to B at some time t, immediately we can see that there is a return or periodic behavior time to t. This is simply because the matrix is symmetric. So if there's a PST from A to B, immediately there is a PST from B to A by symmetry of that matrix. And hence, you can just put these two together and then get a return or periodic behavior at time 2t. Okay. All right. So PST implies periodicity in some sense. Okay, so I think I should mention quickly this property of monogamy here, and then I'll hand it to Sabrina. So this is an observation made by Kay, where he observed the following. So if you have a graph where there is PST from A to B, and somebody tells us there is a PST from A to C as well, then this implies there is no other choice here that B has to equal to C. But the caveat here is this is if we use adjacency matrices that are real symmetric. So in this talk, what we are going to do is we're going to see some violations of this property, some violations. With this property. And essentially what we're going to do is look at graphs whose adjacency matrices are no longer real, symmetric. So we're going to change this, and we're going to do this in two parts. So Sabrina will look at oriented graphs, which you will define soon. And I will look at something a little bit general, and it allows for a full Hermitian. Okay. So Sabrina, go ahead.
Great. So if I can scroll, there we go.
Sorry about that.
Yeah. So if we consider an oriented, I do want these to be thinner. I apologize, but it makes sense with my handwriting. So if you have a graph with every edge having an orientation, then there's a natural way to define an adjacency matrix, which is that there's simply a 0 if there's no edge incident to that, if that edge isn't incident to vertex. 1 if there's an edge oriented away from the vertex, and a -1 if there's an edge oriented into the vertex. And this will be a skew symmetric matrix. So we'll have eigenvalues with no real part. And for the purposes of the quantum walk, we can define it as long as we have a Hermitian Hamiltonian for physical reasons that I won't get into. And we can make this skew-symmetric adjacency matrix Hermitian just by adding an I to it. So we define the quantum walk U of t to be the exponential of minus I t times the Hermitian IH, which just simplifies to be the exponential of TA. And one nice aspect of this is that the quantum walk therefore will be real. And from this you can get various nice properties, including that the phase factor, which in the undirected case can be any complex number of norm 1. Here it just has to be plus or minus 1. So this is non-monogamous because at time 2 pi over 3 root 3, the matrix looks like this. At time twice that time. And at 3 times that original time for perfect state transfer, we have that matrix is again periodic. So here, and I'll just redraw the example graph in case you forgot it. We see that we have perfect state transfer from A to B at time 2 pi over 3. Perfect state transfer from A to C at time 4 pi over 3. And this perfect state transfer from A to A at time 2 pi over root 3. I think I was mistaking the times earlier, but they're written there. So this is something that's very different than what can happen in the real case. And there are 2 ways of generalizing this. You could say that while it's happening between any pair of vertices, which is what Tina will talk more about. For my purposes, I think that, say, well, this is happening on a set of size at least 3. And what's happening to make this perfect state transfer occur at all? What's happening to make it happen on this largest set? And that's what I'd like to address. So the first thing we need is a tool that comes up in studying these quantum walks, which this is this notion of strong co-spectrality. So when we have the quantum walk, we can use a spectral decomposition to see that the sum over all of the eigenvalues of e to the t theta r times the corresponding spectral idempotent times the characteristic vector of A is equal to this phase factor times, if we sum over all of the spectral idempotents, we just get the identity. Times the characteristic vector for B. And that's just the definition of perfect state transfer. We can see that if we won't necessarily care about all eigenvalues, because not all of them will affect this quantum walk here. So we define phi of A, the eigenvalue support, to be the eigenvalues that we do care about. That is, the eigenvalues where the corresponding spectral idempotent applied the characteristic vector of A is not zero. And that's the zero vector. So then using the spectral idempotent, we can rewrite this as saying that for all eigenvalues in the eigenvalue support, e to the t theta r times er times the characteristic vector of A equals plus or minus er times the characteristic vector of B, which we can then rewrite in this way. And we say that the thing we really care about here is that this is just some complex number of norm one. If we know more about the quantum walk, then we know what this time t is and what that is. But if we don't know that, all we know is that the spectral idempotent of R applied to A must be some phase factor or some complex number away from this idempotent of the characteristic vector of B. And that is a property of the graph and the corresponding matrix that was chosen. So we say that vertices A and B are strongly cospectral if for all eigenvalues that are in the eigenvalue support, there exists some number QR of AB, which is between -1 and 1, such that that's a little small, I apologize. Essentially, you have this, that they differ by this complex number of norm 1. And this will be a property of the underlying graph and matrix. It'll be related to the ABth entry of the spectral idempotent. And this is obviously a necessary condition for perfect state transfer, as we showed in our earlier calculation. In fact, this is also a condition that we can use to rework the definition of perfect state transfer to get an equivalent characterization. So if X is an oriented graph with vertices A and B, and there's perfect state transfer from A and B, if and only if vertices A and B are strongly cospectral, And you have this parity argument relating to that QR of AB. So this is a characterization, but it has the same failing that, or same problem that the original definition of perfect state transfer has, in that you don't know anything about what the time t is. And in the case that you're working with a real symmetric matrix, you can figure out, try and characterize when a vertex can be periodic, look at half that time, and then you know that you must have perfect state transfer at half that time or not at all. So let's try and do something similar and see how that goes. First of all, let's look at the characterization. So the same way that we did the decomposition before, we can get that summing over all eigenvalues of e to the t theta r times the rth spectral idempotent times the characteristic vector of A equals plus or minus e to the r. And since we're periodic, we're again looking at the characteristic vector of A. Which means that, again, just considering each of the idempotents individually, you then get that e to the t theta r needs to equal plus or minus 1 for all eigenvalues in the eigenvalue support. And it'll be a constant whether it's plus or minus 1. We don't need to worry too much about that at this point. So in other words, for theta r, theta s in the eigenvalue support. And let's add this condition that theta s not be equal to 0, because that'll be useful in a moment. Then we get theta r, t theta r must be some integer multiple of pi, and t theta s must also be some other integer multiple of pi. So therefore, if we divide these two equations, we get that theta r over theta s must be rational. And we call this the ratio condition. There's a similar ratio condition for real symmetric matrices. It's actually a little bit more complicated. Here you can take advantage of the phase factor being plus or minus 1 to get this simpler condition. We can show that this is true through some algebraic manipulation if and only if there exists some square free integer delta such that for all eigenvalues in the eigenvalue support. There exists some integer, MR, so that theta R is some integer multiple of the square root of minus delta. So every eigenvalue in the eigenvalue support will be an integer multiple of the same the square root of the same square free negative integer. And that you can, like I mentioned, it's just algebra to show that. And you can show that if that's true, then letting t equal 2 pi over the square root of delta, then for all eigenvalues in the eigenvalue support, et theta r that's just going to be some integer multiple of 2 pi. So it just becomes your spectral idempotent times the characteristic vector of A. And therefore, if you have this condition, you have that vertex A must be periodic. So we have this if and only if condition of the periodic ratio condition, and every eigenvalue in the eigenvalue support is an integer multiple of the same square free integer. And through a little bit more work, we can come up with a clever time t that there's perfect state transfer, so you can in fact have a phase factor of -1. But this is a characterization. It's a fairly nice characterization, but we still have the problem that we don't know necessarily that there won't necessarily be perfect state transfer at half the time of the period. We saw that in an example of K3. Is it even true that perfect state transfer implies the graph must be periodic? And let's make this interactive. Let's make you guys answer it. You know, if you could share that link.
Okay, everyone. So Tina is going to put a link in the chat, and you can all go to this website and vote. Actually, I can just do it maybe. This should be the right link.
I'm confused by why the numbers were going down and up by 1%. We don't have that many people.
Yeah. Can you not see how many people have voted?
I can see what you see, so.
I can track it, but it's in the settings.
Oh, I see. Okay. Okay.
Sabrina, do you want to go back to the slides?
Yeah.
Okay.
So, seems like most people believe that this is false. So, you don't really need more convincing of to think that. But here we have part of the fact that perfect state transfer appears, part of the condition for periodicity is that you know that if it occurs, there must be some rational time of 2 pi over the square root of this delta. This is the time that perfect state transfer appears in this graph, which you can see is not a rational multiple of pi over the square root of 7. The arc cosine of 3/4 is very much not a rational multiple of pi. However, despite majority opinion and this graph not behaving the way you'd want it to, it is in fact true. And I can sketch a proof quickly using this theorem of Gelfand-Snyder, that if, in transcendental number theory, that if alpha and beta are algebraic, alpha does not equal 0 to 1, and beta is irrational, then alpha to the beta is transcendental. How could this possibly help us? Well, if we have perfect state transfer, then we know there is some time t, such that e to the t theta r times er times the characteristic vector of A equals plus or minus er times the characteristic vector of B. Now, the entries in the spectral idempotent are closely related to the eigenvalues. In particular, you know that they must be algebraic. So this is algebraic. This is algebraic. And that means that for theta r, theta s in the eigenvalue support, e to the t theta r, e to the t theta s are algebraic. And if theta s does not equal 0, then we can write e to the t theta r, or e to the t theta s is equal to e to the t theta r raised to no, I lied over there. E to the t theta r is equal to e to the t theta s raised to theta r over theta s. So we know that this left-hand side is algebraic. This is algebraic. Well, this is the ratio of 2 eigenvalues. It had better be algebraic. This is, theta s was not equal to 0. So this is not equal to 0 or 1. Therefore, the only possibility is that theta r over theta s is rational. So it is in fact true that perfect state transfer implies that the vertices are periodic. However, this doesn't give us any useful indication of when the time occurs. So let's go back quickly to the example we had of K3, where we knew that perfect state transfer occurred from A to B, and then from A to C at twice that time, and A to itself at 3 times that time. One of the things that's happening here is that there's a automorphism. P tilde taking A to B, B to C, and then C back to A. And this can extrapolate in general to get that if you have an automorphism P tilde such that you have PST from A to P tilde, then you have perfect state transfer on the set A, P tilde, A applied to A, so on and so forth, until you get the order of that. And with that in mind, we can come up with a characterization that if you have an oriented graph, then you have this multiple state transfer on the set of vertices that are under the image of the automorphism. If and only if your vertices in the image are strongly co-spectral, the vertex is periodic, and the eigenvalues satisfy a certain parity condition, which is just, you know, the time the perfect state transfer occurs. Therefore, you can figure out, using our previous characterization, what properties the eigenvalues need to satisfy. And if you're really curious, there it is, but the main thing to know is that it works. And then I'd just like to conclude my part by showing that the oriented graphs on 3 vertices are not the only, K3 is not the only example. We have this graph as well.
Can you zoom out a little bit? I think you can do it in like view.
Yeah. And then I think I'll pass it back over to Tina.
Okay, thanks. Right, so let me. Okay, so continuing from what Sabrina did. So we have this. Oops, I should go back to pen. Ticker. Sorry. All right. So with time remaining here, let me just. Okay, so we were looking at this. C3 essentially, but oriented, where we put I on the forward direction, and implicitly there's a minus I going back, right? This matrix. So let's see. So this is A, B, C. So A to B, right? B to C, C to A, and to make it Hermitian, we have to simply just fill it up with the complex conjugate. Okay, so this is the matrix. But you can also view this. So this is what Sabrina actually did with Chris. So essentially view this as a I times a skew symmetric matrix in some sense. Right? So this is skew symmetric. But this matrix itself is Hermitian. So in some sense, you can view this skew symmetric structure as the oriented structure, right? Oriented graph. So what's interesting about this example, as Sabrina covered, mentioned, is that there is PST. PST exists between every pair. Right? So the question now is, can we generalize this to larger graphs? So are there other graphs? It's a question. Are there other graphs with the same property? Yes. And let's say this is what we would call universal property. PST property. So the definition is here. There exists PST between every pair, right? So let's say this is what we call universal PST. So and we have an example of this. So the open question is one of the open question we have is is this the only example with weights from plus minus I? This is open. We don't know the answer to this. So so essentially, if you are allowed to only use plus minus I for the weights, then is it true that this is the only example with this universal property? So we don't know the answer to this. But it turned out that there are examples of graphs with this universal property if we allow to relax this structure, this oriented structure, to arbitrary Hermitian matrices. Okay, so let me just state a few facts, and I might not have time to go through them. So what we know, this is from some joint work with some RU students, is that if a graph has this universal structure, universal PST property with Hermitian adjacency matrix, A, for example, then we know some properties of this graph. Well, the matrix that has to hold. One property is that A is unitarily diagonalizable. Diagonalizable by a flat matrix. Flat here means the all entries have the same magnitude. A good example here is the discrete Fourier transform matrix. Okay? So the second property we know is A has distinct eigenvalues. And this is true for arbitrary graphs with arbitrary Hermitian matrix, as long as it has this universal PST. Okay, so this is two strong conditions. So I think, okay, so let me check time. So we have, Sophia, we have about 3-4 minutes, is that right?
Sure, yes.
Okay, so I probably don't have time to prove this, although I was planning to show this one. But so let me maybe just mention some other actually. So yeah, it would be too long, I think. Okay, so let me just mention some other some other observations and questions that we have here. Okay, so so there are some questions that came out after this sort of work. So the most examples we know tend to be circulants. So it made us suspicious, and then ask the following question: if graph G has a universal PST property, then G is a circular, or rather the matrix is a circular. So we were suspicious that perhaps only circulants can pull this off. So this turned out to be false, because there are constructions of non-circulants that has this property. But the funny thing is, most of these constructions are actually showing that underneath this construction there is a circulant lurking behind. And I'm not defining this word pseudo properly, but it is essentially based on a circulant that is essentially just shifted. Okay. So in a sense, it might still be true that only circulant type constructions can produce these universal PST graphs. So the other question we had was, so once this is settled, we had this other question where if a circulant G has this property being universal, then it has to be dense. Actually, the matrix, we mean here the matrix. The matrix is dense, meaning it cannot have any, it cannot afford, other than the diagonal, that is, cannot afford to have any zeros. Right. So this is almost true. So what we observe in this other work, so this is work with some other students. What we observe is this is true, true if the order of this circulant, so this is circulant G of order n, is prime squared or power of 2. And we have a construction where it's definitely false if n has 2 distinct prime factors. And there is a gap here. So there's a gap between this true and false, and the gap is we don't know what happens when n is a prime power that is not a square. So we don't know what happens when this is a prime that looks like this, where n is at least 3. So there is this gap. So there is this case where we don't know whether it swings to the true side or the false side. So this is still open as well. Okay. So this is open. Okay, so and if I may, so we are running close to running out of time. Let me mention one more question, if I may. And this comes back to what Sabrina asked in the poll. So the question here is the following. So suppose you have a graph G with some arbitrary Hermitian adjacency matrix. And suppose we are told that there is a PST from A to B. Sabrina and Chris proved that in the case of G being this complex-oriented graph, where so this is let's say A here. So here's A, and this is skew-symmetric. In this case, it's true that we can always come back. So we can always come back to A. So return to A is guaranteed. To A is guaranteed in this case. It is so, and the proof in a sense requires Gelfand-Schneider. So the question is, what happens in general for arbitrary Hermitian? Is this still true or not? And this is open, as far as I know. It would be interesting to construct an example where you can go from A to B as a PST, but you cannot come back. And for the real symmetric case, we always take this for granted, that you can go from A to B and always come back because of the symmetry. But in the general Hermitian, it is not clear. Okay, with that, I think I will stop because we have only 1 minute left. Thank you for your attention.
Okay, thank you. Do we have any questions for Sabrina or Tino, or both?
I have a question. So Tino, like in your first question, you talk about the flat type 2
Which
and
one,
distinct eigenvalues.
This one, yes.
Yeah, this one. Yeah.
Yeah.
So my question is like, so finding like a flat type 2, so you just take a complex Hadamard matrix, right? And finding Hermitian matrices that has distinct eigenvalues, so it's easy, right? You just take the columns and take the projection, and you take the linear combination, then you can basically manufacture your A. So if I have such a matrix, what do I need to check to see if it has the UPST?
So yeah, so there is something we have here in this other work where there is a dance that has to happen between the times and between every pair and the times PST between every vertex in the pair. There is an equation that has to be satisfied that depends on the flat entries in that flat matrix. So there is this condition that can be checked.
I see. Okay. Cool. Okay, I'll take a look at that paper.
Yeah, I can point you out to that condition. Yeah.
Okay. Thanks.
Good question. So Ada, are you asking whether this can be polynomial time verified?
Oh no, I'm just asking like what needs to be done. You're way ahead of me.
Okay.
Yes. Yeah. Well, my next question, I don't know if it makes sense, but so when you talk about the two distinct prime, it reminds me of some of these proof of like PGST or PGFR, where like for two distinct prime you would have kind of a way to either rule it out or I think it's ruled out. Yeah. So I'm just wondering if the proof you have there for the false at the bottom of the screen, if it has the same flavor.
Yeah. It relied on some fact that we found in algebraic number theory, but none of us are experts in algebraic number theory. So I suspect that's the reason we couldn't resolve that question for prime power. That's not a square.
Okay. All right. Okay. Thank you.
Thanks.
I have a question.
Yes.
No, mind. Do you have a good way of generating examples of graphs in the unweighted case that have this PST?
In the unweighted case, what do you mean?
Just Well, I mean, you have a few examples, but is there a good way to find other examples or a nice construction
No.
in the way that we have it for for traditional PST?
No, nothing new here.
Products and things like that.
So yeah, there are like standard constructions that you can use using essentially graph products and sometimes joins. So yeah, so this is a good question, because the interesting thing is to ask what properties can preserve PST in some sense. What graph operators can we use to preserve PST? Because then once we have small examples, maybe we can produce more if we know the graph operator preserved PST. So a famous example is actually the Cartesian product. If you take the Cartesian product of graphs with PST, then you'll still have PST.
Right.
So you can generate lots of these. But it's not clear how to do it with this universal PST things, because it seems like the construction has to be one-shot global. You can't build them slowly. This is the annoying thing.
Yeah. And there was a large example, that graph that Sabrina showed. I don't know if there was a better way of thinking of that in terms of if it was composed of some sort of smaller graphs that maybe exhibit I wasn't sure if there's a better way of thinking of this than just
Not that we found so far.
Well, you can write out the adjacency matrix. It's got a fairly nice pattern. So you can give a nice description in the drawing.
Is it a product of some sort? It looks like a product.
How vague you want of some sort to be.
Yeah, well I'm not sure about the arrows, but it looks like a product to me.
It isn't a product, but
Oh, okay.
But it is built up from two smaller graphs.
And there's a nicer drawing of it in the paper. It's a bit clearer to see what's going on when it's not hand drawn.
I don't think it's a question of the drawing. I think it's just that there are a lot of arrows, right? So
Yeah.
they're one directional. So.
Well, the one thing that might not be easy to tell from this is that all of the vertices that are filled in have 4 arrows pointing out and 1 pointing in, and the reverse is true for the blank circle. 5 pointing in and 1 pointing out.
Okay.
I can count. So there is something in that all of the vertices that exhibit PST have the same out degree.
Oh, okay.
But
Don't you get PST on both sets of 4?
yes.
Yeah, so you've got 2 sets of 4 and you've got PST within each set. Yeah.
Yeah.
Okay. Yeah, I get, maybe there's is there some nice I don't know, some sort of maybe automorphism plus scaling that will switch the vertices?
If you're dealing with oriented graphs, then the right automorphisms are not permutation matrices, they're monomial matrices, so signed permutation matrices.
Right.
And in the examples where we get this state transfer, what's happening, especially in universal state transfer in particular, the U of t at the critical time is a signed permutation matrix, and to be universal has to be a signed cycle. So if you're going to insist on universal state transfer, then at time t, U of t will be a signed cycle, and this is presumably why they tend to be circulars.
Okay.
Now, there's a gap between there and stuff that Tino was talking about. I mean, I don't really, I have a feeling you should be able to do more with this, but I can't, haven't so far. So in a certain sense, the question you might ask is, I a sign graph, is there a time t in which U of t is a sign permutation matrix? Now that's weaker than asking for universal transfer, but it is asking that that you've got the vertices partitioned as sets, and there's transfer between any two vertices in the same set. And so Sabrina's example has that property, and Tino's example is universal. So that's a weakening of universal. But I haven't been able to get any mileage yet by assuming that U of t is a monomial matrix yet.
I have one more quick question. I don't want to monopolize the question session if someone else has a question though. But have you looked at any notion of like fractional revival on with this sort of structure for your adjacency matrix?
What are you asking?
Oh yeah, anyone, I guess.
The answer is no, but that's a good question. So your question essentially is if there is fractional revival on these oriented graphs, right?
Yeah, or if you could make some sort of sense of what some necessary conditions would be, or if there's sort of if you could build up the analogy the same way.
Right. No, that's a good question, actually. It should be investigated for sure. Yeah.
Yeah, thank you. I really enjoyed the talk, and I like the format with the. It's nice to see a board talk after so many slide talks. Thank you.
Yeah, I agree. I really like the board talk actually. Do we have any other questions? I actually wanted to just ask quickly, what if you could explain a bit more what pseudo-circulants are.
So it is, so essentially, if you look at the flat matrix that's defined in that construction, it's actually, there is a specialization where you can recover essentially the discrete Fourier transform matrix, but it's almost like just shifting a little bit. The other intuition is if a circulant has a universal PST, then the time in which the PST visits happen has to be evenly spaced. So if you want to break this pattern, you can. You essentially just don't have this uniform spacing of times. So you can make one longer and compared to the other. So there is some shifting going on, but essentially the basic framework, I think, is still just a circulant. This is my sense. So yeah, I apologize. I mentioned pseudo-circulant in a very non technical sense. It might have a technical meaning somewhere else, but yeah, it just felt like a circulant that's being shifted a little bit here and there.
Okay. Okay, thank you.